Now we'll see what is Ehrenfest theorem. Ehrenfest theorem states that the expectation value of quantum mechanical operators such as position and momentum or any dynamical variables follow the equations of classical mechanics. That it shows that the time derivative of the expectation value of position and momentum are related to the expectation values of the momentum and force respectively, like Newton's law of motion. It provides a relation between quantum mechanics and classical mechanics, demonstrating that quantum systems behave classically on average over time. It gives a correspondence between the motion of classical particle and motion of wave packet. It is derived by Ehrenfest in 1972. So here there is a limit. In the limit, when the wave packet associated with the particle reduces to a point, one expects the particle to behave like a classical one. To derive this, consider a one-dimensional motion of a particle of mass m. The expectation value of position x is derived is we can write it as integral psi star x psi d tau. So the time derivative of the expectation value of x is given by d by dt of the expectation value of x is equal to dou by dou t of integral psi star x psi dx. So if you differentiate this, then we can get dou psi star dou t x psi plus psi star x dou psi by dou t. So if you substitute this in the equation 2, we can get it is integral from minus infinity to plus infinity. Dou psi star by dou t x psi plus psi star x dou psi by dou t into dx. So now you take the Schrodinger equation. So it is I h cross dou psi by dou t is equal to minus h cross squared divided by 2m dou squared psi by dou x squared plus v psi. So from this we can derive dou psi by dou t is equal to I h cross by 2m dou squared psi by dou x squared minus I v by h cross psi. So if you take complex conjugate of equation 5, we can get dou psi star by dou t is equal to minus I h cross by 2m dou squared psi star by dou x squared plus I v by h cross psi star. Now you substitute these values, equation 5 and 6 in equation 3, and then we can get it is minus I h cross by 2m dou squared psi star by dou x squared plus I v by h cross psi star into xi plus psi star x into I h cross by 2m dou squared psi by dou x squared minus I v by h cross psi. The wave function and its derivative tends to 0 as x tends to infinity. So this value is equal to 0 and we will get minus integral from minus infinity to plus infinity dou by dou x of xi dou psi star by dou x into dx. Once again, if you differentiate, use the same formula. Integral from minus infinity to plus infinity psi star minus I h cross dou by dou x into psi dx. So this minus I h cross dou by dou x is nothing but your position momentum operator. So it is m, the time derivative of the expectation value of x is equal to the expectation value of momentum. So in the limit, when the wave packet associated with the particle reduces to a point, the expectation value of x becomes x and the expectation value of p becomes p. So the equation 10 reduces to a classical equivalent, that is m dx by dt is equal to px. Next, you take the expectation value of momentum p. So it is momentum operator is minus I h cross dou by dou x. So the expectation value of p is minus I h cross integral psi star dou by dou x psi dx. Once again you take the time derivative of the expectation value of p. Then you will get this dou psi star by dou t, dou psi by dou x plus psi star dou by dou x of dou psi by dou t. So once again use the Schrodinger equation, that is dou psi by dou t with a corresponding complex conjugate. Then you substitute this in equation 13, we can get it is equal to minus I h cross by 2m dou squared psi star by dou x squared dou psi by dou x minus dou cube psi by dou x cube plus I by h cross v psi star dou psi by dou x minus psi star dou of v psi by dou x. The wave function and its derivative tends to 0 as x tends to infinity. So this value is equal to 0 and we will get minus integral from minus infinity to plus infinity dou by dou x of xi dou psi star by dou x into dx. Once again, if you differentiate, use the same formula. So in the limit, once again, when the wave packet associated with the particle reduces to a point, the equation 13 becomes the Newton's second law of motion. So now you generalize this equation 10 and 19, we can obtain m d by dr by dt. D time derivative of the position is equal to the expectation value of momentum, and time derivative of the momentum is equal to the expectation value of the force. So this is called Ehrenfest theorem. It gives the quantum equivalent of equation of motion of the classical particle. Thank you.